So today we're going to talk about AI in industrial operations. So meaning that we are interested into looking at what AI and machine learning can do for you in the shop floor, in industrial settings. But the first questions one might ask is, why do we need AI/ML in industrial contexts and shop floors? One of the reasons is that we have been talking a lot about digital transformation, and these transformations doesn't stop at the shop floor door. It's increasing across every manufacturing process-centric industries, be it for discrete manufacturing, assembly line for aircraft, process manufacturing like chemical, oil and gas, energy production, mining operations, etc. However, this industrial faces unique challenges that are coming from the context, the industrial context. One of the first is, of course, we're talking always about that in IT settings already, is integrations of data from multiple, let's say, multiple data sources. In the case of industrial settings, we have to integrate data from multiple machines. And in the industrial context, we have sometimes hundreds of different machine communication protocols. We have many on-premise software applications that have been running sometimes for decades without an issue. We have legacy automation systems. So getting access to data after a timely fashion can be already another level of challenge. With that said, once you actually have these all unstructured streams of machine data, it can be very difficult to organize and contextualize. The data coming from one machine needs to be contextualized with data coming from your ERP system, for instance, or it must be contextualized with another machine coming from another production line in another factory. And if you want to scale and manage your processes, your manufacturing processes across the whole world, that's another level of complexity also. Huge companies like Unilever or Procter & Gamble have hundreds of production lines around the world. If you have to design an AI/ML systems for each of these production lines, this is not scalable. So the ability to scale not only across your industrial equipment, but also across your whole device fleets and data across numerous sites, and potentially from remote sites with limited connectivity, can be very challenging. Another thing that we actually see a lot more in industrial settings, and the reason why we didn't have a lot of AI in industrial operations until now, is the fact that for real-time decision-making, we actually have a very low, if not minimal, tolerance for latency on the decision-making, and especially due to the speed of production. If you have to throw away a piece of hardware that you built, and you are actually, I don't know, maybe manufacturing hundreds of them in a minute, then you need to be able to take these decisions very fast. Last but not least, we are seeing a lot of questions about security. How do we keep industrial operational assets and their data secure? Is not necessarily the same challenges and impact than with the GDPR, with personally identified informations, but we're talking about the very industrial secrets from a company, how they manufacture their product, what is the quality of the production lines in average, what is the uptime, and this can have major impact either on the public opinion or from investors' opinion. So all of these challenges exist at some level for consumer industries, but they are scaled in a different way, and sometimes in a largely global ways for industrial operations. One, let's say, challenge also is that most of the time you don't actually deliver an AI into a shop floor to solve a simple problem. You want to improve your uptime. You want to improve your overall efficiency. You want to reduce your production quality to remove any non-quality products being delivered to your customers. And to do that, most of the time, you need multiple AI services working together. In an assembly production lines, you might actually have something very simplified that looks like this. And you might have hundreds of, let's say, equipments. Some of them might be very old. I've visited factories where some equipments were actually running for 100 years. So how do you enable these 100 years of sets to actually be smart? How do we collect vibration and temperatures, for example, on a stamping machine that is 100 years old? You might actually have also been collecting hundreds of signals for decades in your distribution system or in historian actually located on-premise in your factory, sometimes for decades. So you actually have a lot of data that are sitting somewhere, maybe not used, or very hard to actually put in context with other data collected elsewhere. You might also have multiple points where you actually need to take pictures, either manually or automatically, to actually support your quality inspection process. You may have already some smart camera on which you need to deploy computer vision at the edge to actually deliver object tracking, or maybe supply chain inventory optimization, etc. And of course, you want to have a single command and control center where all of these insights can be actually merged together so that you operators, plant manager can actually take the right decisions to actually improve the operations. So all of this put together is actually what AI can look like into production systems. So after this introduction, let's have a look at some lessons learned from shop floors. So in the past 5-6 years, I was lucky enough to actually travel to many shop floors from many different customers in different industries. I've traveled from the UK for steel manufacturing to Central Africa in mining facilities, to the biggest shampoo production plant in Europe, in Eastern Europe, etc. So, and we had a lot of lessons that we actually learned from these shop floors. Every factory is different. Every production line is different. Even within a single company, if not a single factory, you will have a very diverse set of skills, pieces of equipment, production practices that you need to take into account. So let's have a look at a few examples. The first one I'd like to have a look at is an aluminum coils producer. So this company is producing aluminum coils in the UK. And these coils are actually used and sold to electrical companies. So these are electrical aluminum and electrical steel production. The overall production process itself, and this is a tiny part of the process, is quite complex. And usually in these factories, you only have very good process engineers that know this process by heart. They know how to optimize it. They know how to run it efficiently. And AI is not here to replace this kind of domain knowledge. AI is really here to augment the operators, the plant managers, the process engineers, and in this situation, even the data scientists in the corporate team. We started actually the discussions with a newly established corporate team who actually had some data scientists available. And what they wanted to do was to build and deploy a predictive maintenance tool that could actually support their everyday operation. And one of the third thing that was actually told to us at the beginning is that the plant is too old. We don't have a lot of data. We want to do predictive maintenance. We don't know yet on which piece of equipment. And basically, after maybe a couple of meetings, we decided to actually go and visit the plant, to actually see the process, understand where some potential data are collected, talk to the actual operators, understand the kind of challenges that they may have. And this first factory visit actually told us three things. One, the plant was indeed very old. This is a couple pictures from the plant. So you can imagine going there and asking, okay, where are your sensors and your nice data? Can I have access to your data set? So yeah, very old, a very harsh environment. So bringing a mobile-based applications without heavy investment would be quite challenging. What we also discovered is that predictive maintenance was actually not the first issue. And that's one key lessons learned here. We talk a lot about Industry 4.0 and predictive maintenance or even prescriptive maintenance. However, most of the time when you talk to operators on the lines or the plant manager, what he wants to do is to produce more or to produce better. Predictive maintenance may be a mean for that, but it's only one of them. And in this case, the first issue that we were actually told about is that this manufacturing process, you see here, you have an aluminum coil and you have the sheet that is actually going through a rolling mill here. And this process generates dangerous snaps. So whenever the speed is not right, or maybe there's a defect in the coil, the aluminum sheet will actually snap, and this can actually be very dangerous for the people around. So one thing is predictive maintenance was not the first topic. Second, although the software used to drive the system was quite old, it had been storing sensors data for at least 5 years at 10 millisecond sampling rate. So they did have data. They just did not necessarily know where exactly and how to leverage it. But the automation engineers at the site were actually telling us, well, we have a lot of data. We don't do anything with them, but we have a lot of data. We actually store 10 years of them now. And our system is able to actually store the past 5 years online. And so basically, we learned that predictive maintenance was not the key topics, although it's very hot. And we will come to that later on. And we also learned that we had a lot of data. That was great. What we did not have, however, and this is what usually a lot of people mean when they say they don't have data, they did not store the timestamps at which the snaps happened. So when did the anomaly happen? They did not store also how long before the anomaly happened they were starting to notice that something was going wrong. And this is where most of the time people will be right. Well, I don't have this kind of data collected because I can go too far in the past. When actually something happened, we correct it. We stop the machines. We make sure that everyone is safe. We don't think first at writing down the timestamp and collecting the actual timestamp at which it happened. We make sure that everybody is safe. So the first I think we had to do in this case was to use some, and we had a lot of data. To give you an idea, the first data set we had was 5,000 signals over 3 years. That was a 3 terabyte hard drive that was sent my way. And we actually used deep learning because we had a lot of data, so it was great to leverage. And we used a simple autoencoder architectures to detect portions of the time series that looked like anomalies, because we knew that nobody would be able to tell us when did something happen a year and a half ago, let alone 3 years ago. So we started to actually demonstrate that the data contained predictive power, meaning are we able to find and then predict when a snap was going to happen? And we did that in 2 steps. The first step was to detect and label the past data. And the second step was to actually build a model to predict the snaps. And when we were working in the plant, the other things we actually learned is what would the operators need for this AI to be actually useful for them. And what they told us that, well, you know, it's dangerous, it's going very fast. So if you give us at least 2 seconds or 2 seconds to the system to be able to stop the machine urgently, we would be happy. Because stopping the machine is not too costly. They would prefer not to stop for nothing, of course, but not stopping the machine when something happens means that the coil snaps, you actually risk some injuries. You have to stop the machines, to cut the coils in 2 parts, re-prepare, maintain the machine. So it's 2 days lost. Whereas stopping the machine and just noticing that nothing is wrong and restarting it is just maybe 15 minutes lost. So basically, they wanted to have at least 2 seconds that we can send to the system. The good thing is that we were able to, using the data, and they had, well, 10 years of data at 10 millisecond sampling rate with 5,000 signals across the whole production line. So that's a lot of data. They also have equipment data, process data, product quality, etc. So we were able to get a reliable prediction actually 15 minutes before it was happening. And keep in mind that one coil, it takes 30 to 40 minutes to produce a steel coil. But the last roadblock we actually hit was that between the moment the data are generated and the moment they are available online, there was a lag of 24 hours. And this was not something that we discovered in time, because we actually asked, okay, do you have data? Yes, we do. In the end, that was great. You have, how much historical data do you have? We have 5 to 10 years. Awesome. Send them away. But the key thing is the availability of this data. They are generating live, but we could actually access them only 24 hours after they were generating. So one of the challenges that they had at the end is to actually make sure that the data gets closer, so that we can actually get the data to make the runner model and get the predictions before something happens. So 2 key takeaways here is, 1, use the Gemba walk, go into the production lines, meet with the operators, meet with the process engineers, the lean leader. There may be black belt and green belt working on continuous improvement projects in there. There will be good people to talk to because they have statistical knowledge. They understand the data. Meet with the automation engineers, understand when the data are available, when they are actually collected. Is there any lag between their availability and where they can actually be leveraged? So getting timely insights can be harder to get than what one thought. I just, so no questions now, Stefan? I'll continue then.
Yep.
Okay.
Was om 1:30.
Okay. So a second use case is we're still staying in metal work. This is from a steel manufacturer, and they're operating an arc furnace. Arc furnaces are operated a lot in mining, in metal working industries, or any kind of area where you need to melt stuff, basically. And these furnaces can be huge. But most of the time, they also consume a lot of energy. And the steelmaking industry makes heavy use of furnaces, blast furnace or arc furnaces. There are quite a lot. I think I remember having a look at how many of them there were in Europe, and we still have around 100 of them in Europe. And in this case, so this steelmaker is producing steel tube, and each batch is around 40 minutes. And a batch can actually consume up to 50 megawatt hour. And this is based on data we obtained from several electrical arc furnace operators, EAF, which means that in a day, you can get an average 20 batches per day, with a batch lasting from 20 to 60 minutes. If you think about it, one arc furnace can consume between 300 and 500 terawatt hour per year to run. And if you take a 6 days a week assumption, and using the amount a 1 megawatt hour cost from an electricity perspective, from a cost perspective, that can amount to somewhere between 25 and 50 million euros per year. So imagine you could actually get, I don't know, 2.5 savings on this. 2.5% means that you reduce the heat time, meaning the batch, the time during which the arc furnace is actually operating, by 1 minute. Doesn't seem a lot like that, 1 minute out of 40. But the saving for one single arc furnace would be in the vicinity of at least €500,000 per year in energy consumption. And of course, you don't have only energy consumption. If you reduce the time it's running, you're also saving on oxygen, additional throughput, you generate additional throughput, so additional revenue. Even if you are actually running your arc furnace in night to have better price, given the price hike we have seen in the past 18 months, this is something that is quite huge. I should have updated it with the latest data. I'm pretty sure it's doubled in the past 6 months. So basically, this particular customer wanted, as you have guessed, to reduce the electricity bill. They already had an optimized contract. They were running these energy-intensive processes at the right time, given their contract. And basically, the main input they had was that they had the metal scrap recipe. So X kilogram of this aluminum grade and Y kilogram of this grade, etc. And based on this, they had some tribal knowledge to get a rough order of magnitude about the length of time a hit was supposed to happen. So an expert would actually have a look at the metal scrap put into the buckets and then pour into the arc furnace and say, okay, given this recipe, I know it takes, give or take, 35 minutes to get a good quality metal that we can use to have a good product at the end. Give or take 10 minutes. In these 10 minutes, this give or take 5 or 10 minutes is what is actually huge. To check if a batch is done, what do? Well, a skilled operator would suit up, open the side door, and look at the fused metal, what it looks like. We'll look at the aspect. And just to be sure, he would let it live, maybe running for a few more minutes to ensure he doesn't have any quality issue. So you can imagine that if you could actually tell this operator, hey, now I believe this this heat here is done. The melt should be quite good. Just give it a look, but I think it's now it's good. You actually augment this operator, and you can actually reduce the need to, or let's say, this tribal knowledge. You don't need to rely on very rare skills with disappearing tribal knowledge. You can reduce the heat's timeline, and this helps also reduce the raw material consumption, the electricity consumption, the oxygen consumption, any additive you need to add into the mix, etc. So basically, what we had was it was between 15 and 20 signals coming from the arc furnace, so different temperatures, different pressure, different vibration data coming from all around the arc furnace. And with that, we also had the data from the recipe, the mix of metals that we pour into the arc furnace. And based on that, we were able to build a model that would just send a notification to the operators telling him when he should be okay to stop the hit. And the idea was to predict when enough energy was provided to the melted metal bath, depending on the recipe and the type of products to be manufactured with afterward. This actually helped save between 1 and 5 minutes per batch. So basically, it helped them yield an additional throughput, an additional batch every couple of days. So on top of the energy savings, this actually helped them to produce more. And as you may know, in this business, everything that you produce is bought. There's not a lot of spare to actually left in the world. So that's something that was very great for them. So basically, it's not a lot, as you can see. We are actually targeting saving 1 minute on a given process. And at the beginning, I remember the leadership was telling us, well, 1 minute is nothing. If you can't reduce it by half, it doesn't avail to anything. But in some processes, what is important to understand is that you have compound interest. You save 10 seconds here, 1 minute there, and then you can actually save overall the whole supply chain. If you use less material, if you still maintain quality, because this also helps increase the consistency of the process. And that is something that is generating a lot more quality. So we have a few minutes left. Wanted to go through one last example from an aerospace manufacturer with grinding operations in CNC machines. So the type of machine, it's detailed parts that are used in the aerospace, and each detailed part goes through the same process. It's manufactured, it's measured, then you correct it with grinding, and then you double check the quality. The idea is to reduce rework and waste. And these pieces would be actually worked in CNC machines. Some of them can be very modern. As you can see here, this is a DMG Mori, very recent one. I think it was maybe 3-4 years old, but some of them are very old. That one is actually doing the same kind of part, but it's 30 years old. And in this case, the topic was really to how do I reduce the need for grindings multiple times after measurement runs. So imagine you manufacture a piece, you measure it, you see that you are out of tolerance. You put it back into the machine for grinding so that you have maybe a better measurement or better plan on some of the surface quality, etc. And then you check again the measurement, and it's not good enough, and you have to go back. So basically here, the key challenge is that you have two machines. One, where you manufacture the part, and the second, where you take the measurements. It's two machines or two positions on the production lines. And basically you waste time at each time. So the question is, are we able to predict when a measurement will be out of specs when we actually, while we're still manufacturing, so that we actually go directly into maybe grinding operations directly if we know that this particular part has a very high chance to actually be of the wrong dimension. And here, what is challenging is to put context, and context is king. And that is one of the challenge also with multiple machines, multiple positions, sometimes multiple people working on the same parts, on the same process, on the same batch of product. Making sure that you have context with ID of the batch or production ID for each part that followed throughout for traceability, but also to make sure that you can associate each data set generated at each point to a given product or given batch. In a nutshell, we've seen a few things. One, just mentioned, context is king. So many industrial operations have MES systems installed, manufacturing execution systems. So there are the ERP for manufacturing, where you can actually collect all the operations and match it with the production ID. batch ID corresponding to each process steps. You can actually put there, populate it with automated systems, or you can actually add in also the manual inputs coming from quality engineers. So building this context, either with an MES systems or making sure you always have an idea to ensure traceability, is probably one of the first things. You will notice that I did not put here that to deploy our industrial automation, you need data, because most of the time you already have this data. You have them in historian system, you have them in SCADA, in DCS, you have them sometimes duplicated in the cloud already or in ERP for aggregated data. So you have this data, but putting them in context is what is challenging. So make sure you can actually have all this data put together and that you're able to build a traceability for all these pieces of data, parameters, etc., from a given batch or product. Use the Kanban work, working with the operators, with the potential end users. What is important for them is to earn trust from AI systems. And building trust is not to replace them. It's really about basically understand how they will use it, how they will adopt it. And last but not least, it's not because an AI can maybe doesn't cut your costs in half that it's not interesting. Build your business case. Make sure you understand the whole impact of a given AI giving you some insights. And there are other things that I could talk about. For example, that one thing is predicting is not improving. I remember I was actually visiting an ice cream plant in Italy near Napoli, and basically one of the first things that they wanted to, some of the people wanted to have is, can you tell us when there will be an issue with the chocolate coating inside of the cones? But then very quickly, we were saying that, yes, based on the data, we're able to predict when the cone will get spongy, which is not very great for customers. Usually they have customer complaints and claims to tackle. One of the things is that predicting when the chocolate coating won't be good doesn't help. Because then you have next question is, why did it happen? And can you make sure it doesn't happen? So predicting something, even if it's a bad outcome, can be useful, but it's not improving your top line, basically. It's not improving the bottom line either, because you actually don't improve the uptime. You might actually request more effort to go and correct something that you predicted. So you need that to be to don't have any false positive. So it's challenging to build AIs that just predict. And that's why predictive maintenance, even though it is very high, is more useful when you can get into prescriptive, meaning that I'm predicting that something is going wrong if you continue doing what you're doing now. But if you adjust this particular set point here while staying in spec, there is a 95% chance that this event will be prevented. And this is what you want to get into, is to get into how to prevent something from happening. And this is what a plant manager will be happy. He needs to produce more, or at least at less bad quality product when he has some. So if you tell a plant manager that you can actually improve his uptime, reduce the scrap or the waste, he will be very happy. Another important things, and I'll stop here for your questions, is to identify actionable parameters. Remember that case with the aluminium coils, where I was telling you that we had 5,500 sensors data here coming from the whole production line. The key things is that not all of them are actionable. Maybe there are some temperatures you cannot change because you don't have any mean to do it on the machine. maybe you cannot change it because from a process perspective, if you reduce that temperature, the product won't be actually usable at the end. So identify very quickly which parameters you can actually act upon so that your AI model doesn't tell you to improve things that cannot be improved, cannot be changed. And that's it for what I wanted to tell you today. So I'll just let you ask a few questions.
Okay, Michael, maybe you can put your camera back on.
Yeah, I was just doing that.
Yes. I already see there's a question of Laura. Her question is, how do you get end users to trust the conclusions provided by the AI services?
That's the million-dollar question. But that's a question that I usually try to address upfront. Really, the question is, what will your end users, what will it take for your end users to actually trust the conclusions? And that's something that most of the time they did not ask this question to themselves before. So it creates an interesting discussion. The second thing after that, there are some processes that comes from the consumer industry, like A/B testing. One of the customers I was talking about, arc furnace, and we were providing something like, hey, you can now stop the heating. How do you trust that this conclusion is good? One thing that the customer actually did is, okay, we have 3 shifts today. Shift 1 will always apply the recommendation from the AI system. Shift 2 and 3 won't change anything on how they work usually. And at the end of the month, we'll have a look at the impact for shift 1. So they did an actual physical A/B testing to test one team actually using the conclusion and 2 others not using the conclusion during a period of time that was long enough. That's something that can be used quite a lot. It's not necessarily always easy to do because you might actually waste some energy, waste some time, you might waste some products. So it is something that is challenging to do. Another thing that you can do before going into A/B testing is to test your data, your systems on historical data, basically telling, if I had this data in the past, the system would have told us that there is an anomaly here. How would you have reacted? And it would have detected this particular anomaly in time or not? What is the impact? So that you can actually get a feeling about the system is able to capture 80% or 90% of the anomalies you want to prevent, while at the same time generating X false positive and how many false negative. And then it's up to you to actually adjust that to make sure that you can actually get the trust. Mm-hmm. One thing that I found works quite well to start earning this trust is to bring the end users and the operators in the room at the beginning. When we do a workshop, he has to be in the room. If not, it will be just another IT tools deployed on him or her without any insights coming from him.